Hello! In this video, we are going to prove the following theorem. Let A and B be objects. Then the singleton set of the ordered pair A comma B is a bijection from the singleton set of A to the singleton set of B. Now, we're trying to show that a set of ordered pairs is a bijection from one set to another set. Now, in general, to show that a set of ordered pairs F is a bijection from a set A to a set B, we could show this in 4 steps. First, we would like to show that F is a relation from A to B. In other words, show that F is a subset of the Cartesian product A times B. And then, after figuring out that F is a relation, we would then show F as a function from A to B. In other words, we would also show that F satisfies the condition that for every element x in A, there exists a unique element y in B, such that x comma y is an element of F. And now, since we know F is a function, we can then show F is a bijection from this set to this set. To do that, we could show that F is both injective and surjective. To show F is injective, we're really trying to show that for every 2 elements, x1 and x2 in A, if f of x1 equals f of x2, then x1 is equal to x2. And then to show F is surjective, we're trying to show that for every element y in B, there exists an element x in A, such that x comma y is an element of F. So, in summary, the first step is to show F is a relation from A to B. The second step is to show F is a function from A to B. The third step is to show F is injective. The fourth step is to show F is surjective. Now, we're going to apply these series of steps to what we're trying to show, right? We're trying to show that this set of ordered pairs is a bijection from this set to this set. So really, we're just substituting F for this set, A for this set, and B for this set. So in step 1, we're trying to show that this set of ordered pairs is a subset of the Cartesian product of this set times this set. And then in step 2, we're trying to show for every element x in this set, there exists a unique element y in this set, such that x comma y is an element of this set. And then in our third step, we're just trying to show that for every 2 elements, x1 and x2 in this set, if their output values yielded by this function are equal, then x1 and x2 are equal. And then in our fourth step, we're trying to show that this statement is true. In other words, we're trying to show for every element y in this set, there exists an element x in this set, such that x comma y is an element of our set of ordered pairs. Okay, so these 4 steps are essentially the outline of what we're going to be doing in our proof. So let's get into our proof. To start our proof, let's give ourselves 2 objects, A and B. And our goal is to show that this set is a bijection from this set to this set. And in step 1, what we're doing here is we're first going to show that our set of ordered pairs is a relation from this set to this set. In other words, we're trying to show that our set of ordered pairs is a subset of this Cartesian product. And to do that, give me an arbitrary element of our set of ordered pairs. I'll call it P. Our goal is to now show that P is an element of this Cartesian product. Now to start, since P is an element of a singleton set, P must be equal to the object in the singleton set. So P is equal to the ordered pair A comma B. And we know that A is an element of the singleton set of A, and B is an element of the singleton set of B. And by definition of the Cartesian product, this means that A comma B is an element of the Cartesian product singleton set of A times the singleton set of B. But since P is equal to the ordered pair A comma B, we can replace the ordered pair A comma B here with P. And so putting this together, we gave ourselves an arbitrary element of this set. And we showed that same object is also an element of this Cartesian product. Therefore, everything in this set is an element of this Cartesian product. In other words, we've shown that this set is a subset of this set. So this completes step 1. Now we're going to move on to step 2, where we show that our set of ordered pairs is a function from this set to this set. So really, this is the statement we're trying to prove. And to prove that, we're trying to prove a statement about every element in the singleton set of A. So give me an arbitrary element of the singleton set of A. I'll call it X. Our whole goal now is to find a unique element in the singleton set of B that satisfies this condition. And first, let's prove existence. To start, well, since X is an element of the singleton set of A, we know that this means X must be equal to A. And we know that the ordered pair A comma B is an element of the singleton set of A comma B. So, since X is equal to A, we can replace the A here with X. Let's also be aware of the fact that B is an element of the singleton set of B. The reason why I'm writing that is because, well, this proves existence, right? If we take Y to be B, well, yeah, B is an element of the singleton set of B. That's what we mentioned right here. And X comma B is an element of the singleton set of A comma B. That's what we have right here. So this proves existence, right? We have found an object which satisfies this condition. But now we would like to show that B is the only object that satisfies this condition, right? We want to show that B is unique. And to do that, well, let's give ourselves an arbitrary object which also satisfies this same condition. I'll call it T. Right? So we give ourselves an arbitrary object T which satisfies the same conditions that B satisfies. The whole goal of uniqueness is to prove that T is equal to B. Well, since T is an element of the singleton set of B, it immediately follows that T is equal to B. And that proves uniqueness. So we've proven that there exists a unique object which satisfies this condition. And since X was an arbitrary element of the singleton set of A, this means for all elements in the singleton set of A, this is true. So we have proven this second statement. So we have proven that our set of ordered pairs is a function from this set to this set. So now that we've shown our set of ordered pairs is a function from this set to this set, now we would like to show that it is a bijection from this set to this set. And we're going to start by proving that it's injective. Now to show that our set of ordered pairs is injective, we're really trying to prove this third statement, where F is really just our set of ordered pairs. And since we're trying to prove a statement about every two elements in the singleton set of A, give me any two elements in the singleton set of A. I'll call them x1 and x2. And the whole goal now is to prove if the output values of x1 and x2 yielded by our function are equal, then x1 is equal to x2. Now, if we can prove that x1 is equal to x2 immediately, then this entire statement is true. So let's just prove x1 is equal to x2, right? Because x1 is an element of the singleton set of A, x1 must be equal to A. Similarly, x2 is also equal to A. So x1 is equal to x2. So we have proven the conclusion of this conditional statement. And if we've proven the conclusion of a conditional statement, that implies that the entire conditional statement must be true itself. So yeah, this is true. And since these two elements of the singleton set of A were arbitrary, this means for all x1 and x2 in the singleton set of A, this statement is true. So this proves that our set of ordered pairs is injective. And now, lastly, we're going to show that our set of ordered pairs is surjective. which means we're trying to prove that this statement is true. Notice we're trying to prove a statement about every element in the singleton set of B, so give me an arbitrary element of the singleton set of B. I'll call it Y. Our whole goal is to find an element in the singleton set of A which satisfies this condition. Now, we know that since Y is an element of the singleton set of B, Y is equal to B. And again, let's note that the ordered pair A comma B is an element of the singleton set of the ordered pair A comma B. And since Y is equal to B, we can replace the B here with Y. And let's also note that A is an element of the singleton set of A. And so, if we take X to be A, well, yeah, A is an element of the singleton set of A. That's what we have here. And A comma Y is an element of the singleton set of A comma B. That's what we have here. So that proves that there exists an object which satisfies this condition, namely A. So we've proven that this is true. And since Y was an arbitrary element of the singleton set of B, this means for all elements in the singleton set of B that this is true. So this proves that our set of ordered pairs is surjective. And that's everything we wanted to prove. So we've proven that our set of ordered pairs is a bijection from this set to this set. And that's exactly what we wanted to prove, so this completes the proof. And so yeah, that's pretty much it for this video.